in India are sent to abroad. So it was taking a lot of time. So in order to have a testing facility in India, they have funded the uh, for the making of a geosynthetic lab. Similarly, the industry has said that why can't we have a civil engineering lab like a soil mechanics, since the everything of the geogrids and the synthetics are used in the pavements. So they have established the soil mechanics and asphalt lab. And apart from this, the BITRA has been basically focused on the textiles. So when it comes to the garments or any technical textiles, starting from the carbon fiber or the conductive fiber or the plasma treatment or the dyeing, and all these testing facilities are previously there. And then we are industry pioneer for the testing of garments, and also for recently we have a project which we are developing a carbon fiber under our director. So this is a basic introduction of our company and then how it has been done. Sorry, 1 second. So when it comes to the payment, this research is basically on the flexible payment. So we all know why we want to have a payment. So when we want to communicate from one place to another place, we want to have a smooth surface riding, and then it should cater the traffic load. In order to have this one, we need to build the road such that it should have to accommodate the traffic load which it was designed. And also the flexible payments are such that they are designed in such a way it should yield elastically, and also it should take the traffic loading whatever there was there. And then the flexible payments are mostly made up of asphalt mixtures, so which is a combination of aggregates and the asphalt. So when you have this kind of roads, there are certain failures are there still, even though the material evolved drastically. Still, there are certain types of failures still we are seeing on the payment. One is the rutting failure, and the second one is a fatigue cracking failure. The rutting failure is nothing but a permanent deformation which happens on a pavement due to the traffic load. There are different types of rutting failures maybe happen. One, if your aggregates or the bitumen is not proper, and the second, the rutting failure may happen if your subgrade is weak or your construction practice are poor. And then we have a fatigue cracking. This happens if you have a very stiff mix due to the higher loading condition or higher traffic, and the payments may fail. There are a lot of solutions are there. We are trying with a polymer modified binder, or we are strengthening the sub bases and subgrade with the geosynthetic geocells. And then we are using a different types of mixtures like stone matrix asphalt. And then we have used the polymer modified binder to cater this. I mean, just to avoid these failures. But still, these failures have been occurring. So we need to address this issue. Then we thought of why can't we reinforce this with geogrids on the pavement, on the asphalt layers itself. So we want to use a geogrids in asphalt layers. Geogrids are nothing but a polyester or a polymeric materials. There are different types of geogrids are there, based upon the manufacturing process, and also the based upon the raw materials. So it starts with polyester geogrids, which are nothing but the PET fibers or the PET, the plastic especially. Uh, then we have a polypropylene extruded geogrids, which are has their own application, and then we have a glass fiber geogrids, which are basically made with the silica and the glass fiber material. And we all know the geogrids are used in a payment application since long time, but these applications are limited only to the foundation layer of a payment. So there are no extensive research has been done. So the geogrids can be used in a flexible payment on a foundation, I mean, on the structural layer. And when it comes to geogrid, there are different types of geogrids like a uniaxial geogrids or the biaxial geogrid. When it comes to uniaxial geogrids, which are basically used in soil applications to improve the bearing capacity of the soil, or when the subgrade is having a low CBR of less than 5, then the geocells and the geogrids like a uniaxial and biaxial has been used with the different types of tensile strength. I will talk about the tensile strength and all in the later part of my talk. So this is a basic idea of the pavement structure. If you see, we have a subgrade, the base course, sub-base course, and the base course, and the binder course, and the surface course. The subgrade and up to the sub-base course, we have a foundation layer where we already using the geogrids and the geocells and the geotextiles also. So these are all comes under a category of the geosynthetics. So where we have improved a lot, even we have constructed a payment by using a geocell. So even if the CBR value is 2 by placing a geocell, and then we have successfully constructed a lot of payments, and that serves the purpose. Now, if the traffic load is high, so if you want to put a grid, why can't we put a geogrid on a pavement layer, just below the surface layer? If you say surface layer in the sense the BC or an SMA layer, or in between the DBM layer. So if you see here, the binder course will be there, and then we have a BC layer. So we want to place a geogrid here instead of somewhere in the sub base or the base course subgrade. So this base course is nothing but our WMA layer. So now the question arises that is there any possibility to keep the geogrids in the below the surface layer? And if it is yes, and what are the challenges we are going to face when you're having a geogrid below the surface layer? So the first thing what we are going to, our objectives or from this research, it will resist the reflective cracking, and then you need to it will give you as a stress relief layer, like basically a SAMI layer, or then it will improve your rutting and the fatigue resistance. But the question is here the bonding strength or the bonding issues. So if you place a geogrid kind of material below the surface layer, is there any bonding issues like a delamination or the whether the load distributions will happen from the surface layer to the bottom layer? That we need to see. So that is one major hurdle in our research. If there was no proper bonding between the geogrid and the both the asphalt layers, then that won't transfer the loads from the top layer to the bottom layer, and that will be a catastrophic failure by placing a geogrid in between that. So we need to address that issue, and we need to see that one. Accordingly, we made our objectives in our research. So first we need to see the feasibility of a geogrids or geosynthetic in asphalt pavement. Whether is it feasible to place a geogrid? And then we have a materials like a tack coat. Usually we'll have a tack coat should be placed above the DBM, and then we will lay the surface layer. When you have that one, what is the role of the tack coat in this one? And the next question will be the what should be the rate of tack coat, and if there was any bonding issues will be there, and if or we need to use a different type of tack coat. These are all things are raised, and then we need to address this issue. Once these are finalized, then we need to see the performance studies of our geogrid reinforced asphalt pavements. So in terms of rutting and in terms of rutting, and also then we need to see whether is this translated into the field and what are the field challenges. These are our objectives of this research. So in this research, we have used 4 types of geogrids. One geogrid is made up of polyester fiber. The polyester is nothing but the PET fibers, where the polyester yarns are weaved or knitted together to make a geogrid, and it has a tensile strength. And the second one is having a backing of a non-woven textile. So this was manufactured so that it will aid in an installation. And then we have a glass grid. The glass grid, as I said earlier, the glass grids are made up of silica material of 60 to 70%. And these are also weaved together to make a grid kind of structure. The grids are nothing but the material, the yarns are knitted or weaved together to have a certain tensile strength. If you lay it on a pavement, it will act as a reinforcing material. And then we have used one more glass fiber geogrid with a backing. So usually when these are all manufactured products from an industry. So we find certain challenges without backing was there in the installation. So we come up with a backing kind of material with a normal GSM, which just aid in an installation, but it won't serve. After that one, it will just degrade into the pavement. So the basic idea of having a non-woven backing at for the geogrid is that. And then these are the properties of our geogrids which I have used, and the aperture size of 225 by 25 mm, and two are made with the polyester and two were made with glass fiber grids. And next comes the coating material. The polyester geogrids are made with a bituminous coating, and the glass fiber materials are made with a polymeric coating. Even the research has also started for the coating also. Since we are using it in asphalt materials, we want to have a coating of the geogrid such that it should be compatible with the asphalt. So when we discussed with the industry, initially they used to have the PVC coating or the polymeric coating, whether but that doesn't have a proper bonding between the asphalt layer. Then we started with bituminous coated geogrids for especially for the keeping it in a asphalt reinforcement. And for the glass fibers, still they are into changing the polymeric coating into bituminous mixtures. I mean bituminous coating. So now we have the geogrids have been finalized for our research, but then we need to, since it was a composite of different asphalt mixtures and the tack coat and the different geogrids, then we need to start with our mix designs. So the basically any asphalt mix with mixtures we need to prepare, we need to follow our MOT and IRC guidelines to make a mix design of this one. Then initially we did our asphalt mix design. It starts with the aggregate. We check the aggregate properties. We kept it the constant, and then we have used a VG40 bitumen since it was a now it was make a almost our highways are constructed with a VG40. Then by that reasons we have chosen a VG40, and then we did a mixed design for the DBM2 and BC2. Why we have chosen the DBM2 and BC2? Because of the laboratory constraint and the NMAS of the aggregates. Since we are when we want to do the rutting test and the fatigue test, there are certain challenges in the laboratory to have the proper NMAS in the mix. So the minimum thickness for the DBM2 was 50, and for the BC2 was somewhere around 25 to 30 mm thick. So because of that reasons, we have chosen these two mixes for our mix. I mean, for our research. And then we come up with tack codes. I would like to come back for the tack code. We have chosen two tack codes. One is usually we use a rapid setting one tack code, which a residue content of some 60 percentage in the bitumen residue will be there. And then we come up with a polymer modified binder. It's not our PMB. It's a different kind of polymer modified tack coat, which is having a high softening point up to 110 degree. And then we fixed a rate of 0.4 to 0.5 kg per meter square. This how we fixed in the sense, I will get back in our test conducted. So then we have conducted the test like interface shear strength, the rutting test, and the 4-point bending, cyclic compression, and the installation damage test, and the field trials. So this is how our composite geosynthetic asphalt reinforcement has been prepared in the laboratory. This is a slab compactor where we can apply the load of 500 to 700 kPa on the specimen. This is you can see the mix will be prepared in a asphalt mixer, and this will be poured in a mold of 400 by 300, and we will compact it with a slab compactor. Once that is done, then we will prepare. This is a sample preparation process. So first we have prepared the DBM of a 50 thick, and then after the DBM is prepared, we have waited for overnight so that it was cooled down, and then we have applied a tack coat. After applying the tack coat, we left it for drying, and the geogrid is placed on a tack coat, and then we have placed the BC which we have already prepared in a asphalt mixtures, and then we have compacted, and then the slab or the sample is removed from the mold. So the slab size was 400 by 300 by 80 thick specimens we usually create for this research. And after the sample preparation is done or the slab preparation is done, the same slabs will be used for the different tests. Like as I said earlier, we are using the interface friction or the bond strength test between the two layers when we place a geogrid, and the rut test has a different dimension, and then we have a fatigue test. So this is the interface shear strength test. This is a one kind of test we have developed in our research to check if you place a geogrid in between the asphalt layer, whether there is any delamination or the bonding issues will be there. This we started with different earlier 2 years back. We started with a different dosage of a tack coat and different types of tack coat by taking one geogrid, and also we tested at different types of temperatures. So here we are showing in this talk, I am showing only about the 40-degree temperature, but we did this test at 23-degree with different types of tack coat dosages. Starts from 0.2 to 1.2 kg per meter square with an interval of 0.3 kg. And then we come up with, say, that 0.5 was giving a bit okay results, and we fix that the tack code dosage for these four geogrids. And then we did the interface shear test on these geogrids. If you see the control mix or without a geogrid, it was 0.4 with RS1 tack code, and it was 0.18 Newton per mm square or MPa for the PMB tack code. So you can see almost all the geogrids are having a similar kind of interface friction or the interface shear strength was results have been so has been there. So we confirmed that there was no delamination is happening for this one. And the tack code dosage which we followed of 0.4 to 0.5 kg per meter square was okay. So we got a lesser result for 0.2, which is our usual standard practice as per the MORTH. And then we come up with a rut test or the rutting test on an asphalt pavement. When you come to the rut test is a permanent deformation test. When a vehicle passes on a pavement which is having a wheel load, that what happens, that will create a permanent deformation. Just like unrecoverable stains will be placed on a pavement, which will of a repeated or a cyclic loading of our traffic load, it will create a rut on the pavement. So we need to check up to how many cycles or up to how many MSA we can have this rutting. So we need to have a test facility. So this is called a wheel rut test, has been conducted on the composite material by having a DBM at the bottom layer and the geogrid, and then we have a asphalt layer, the BC layer on top of that one. So you can see the shear failure if the rut test has been completed after 20,000 cycles. You can see on the screen here we can see there was a crack formation or the. So if your base course is weak or your mix is weak, so that will lead to a lot of rut. And these are the results for our from our research. So this we conducted in a dry condition at a 60-degree temperature, and the tire pressure of 700 kPa is applied on the pavement, and we went up to 20,000 passes. So we want to see the control mix where we got 15.01 of rut after 20,000 cycles. When we have the geogrid reinforcement in the pavement, we have a 4 rut and 4.32, and for glass grid it was 6 and 6.45. We can considerably the rut resistance has been improved by placing a geogrid that we can see. So these are the images of the specimens. So we can clearly see this has a lot of rut, and then there was a crack formation was also there at the wheel path. When it comes to other geogrids like G60, G50, or the polyester grids of with backing and without backing, and the glass grid with backing and without backing. So the rut depth is almost 50% lesser than the control mix. And this is we can see the cross section of a specimen. So you can see here there was no shear failure or something was there. When it comes to this one, we have depression kind of things, and a lot of cracks has been formed on the bottom layer and also on the top layer. So this says when you have a geogrid reinforcement in asphalt layer, that will resist the rutting, and also the shear failure may not happen that quickly, even after the 20,000 cycles. So, and also it will this payment has been cracked prematurely or before the rut slope or whatever we calculate before that one is very high for this unreinforced section. So then we come up with a rutting coefficient. Suppose when we want to have a geogrid, then in the market or the companies will start manufacturing with lot of geogrids. So we want to have a coefficient. So which geogrid is performing better than other one, or what types of number of grids should we have that one. And by considering all these factors, we come up with an equation called geogrid rutting coefficient by taking the rut depth and the wheel load. Suppose in this our case we have used a 0.7 as a kilonewton as or 700 kPa as our wheel load, and then we have a rut area. So that nothing but the rutting specimen area. So here we have used a 300 by 300 specimen, and then the tensile strength of a geogrid. Suppose we have a tensile strength of geogrid of 50 kilonewton per meter, and then we have a 100 kilonewton per meter. These are manufactured only for the asphalt reinforcement. They are up to now the industry is manufacturing up to 500 to 600 kilonewton per meter geogrids for the soil applications. So we are consider all these factors, and then we come up with a coefficient by considering the air voids in the mix. Why we are considering air voids in the sense that this one, if you see, uh, the specimen needs to have a six. If you see this one, the specimen should have a 6 plus or minus, sorry, 7 plus or minus 1 air voids. So suppose if you calculate air voids of 6.2 percentage with a 7.8 percentage, so that will affect our coefficient. So we come up with a factor of air voids also, and then the number of rips. Number of rips are nothing but if you have a geogrids. So I can show it here. So these are number of rips. So if you see, these are the number of rips on the biaxial. So how many number of rips have been in 300 by 300 area? Then we have considered that factor also by making this equation. And then the air voids has been there. So by based upon this one, we come up with a rutting coefficient value. Suppose if it is 0.1, it was excellent, and then anything above 0.4 will be poor, which cannot be used in the geogrid applications. So based upon that one, we for our 4 geogrids, we have calculated the rutting coefficient. So which says the G60 has given a very good rut resistance of 0.09, but G50 has given a bit higher than the G60, and even the glass grids are performing good since that whatever the tensile strength of the glass kits are nearly 100. But even though it has a 50 kilonewton strength, it has a high number of rips, and also it has given a good resistance compared with the other grids. Then one we did the rutting test and we have get the good values when compared with the control mix, and then we come up with we need to check the how the geogrids are performing towards the fatigue or the crack resistance. Then we need to do a 4-point bending test. This is a 4-point bending fatigue test which we conducted as per ASTM EN 1269724 specification. Here we have a slab we will prepare a beam, and then it will be placed in between the 4 supports, and the load will be applied at the center of the 2 supports, and then it was in a pure bending moment without any zero shear. So we can do this at our chosen temperatures. Since we can see here we have a temperature cabinet, so the whole testing can be done at a specified temperature. We did this test at 20-degree temperature. So the whole testing will be test instrument will be placed in a temperature chamber, and this is a number of cycles to failure, and then we will calculate the NF or the fatigue life of a pavement based upon the strain we have applied, and also what will be the degradation constant we'll get from the graph. And this is how the specimens has been made. So we made a slab with the asphalt reinforcement, and then we have the grid and the BC and the DBM. After that one, the slabs will be placed here. So you can see here, and this will apply the load at 2 points at the midpoints. You can see here the load will be applied in this junction here with a constant frequency and the constant strain rate. So the loading condition was 50 heads. So, and then the constant strain rate, this test is run at the constant strain rate from 80, 200 and 500 micro strains. So first we'll done the test at 80 micro strains, and we are saying after how many cycles the specimens breaks. The failure criteria we have chosen here is a 50% reduction from the initial stiffness. So initially the pavement will have a modulus of the stiffness value K. So from that value, how much cycles it took to reach the 50% reduction. Suppose if it was 2000 is your initial stiffness, how much cycles it's taken to reach the 1000 stiffness value. And then we have conditioned the specimen at 20-degree temperature for 4 hours, and the whole testing is done at 20-degree. So you can see these are our strain levels. So starts from 80, and then this is at 200, and then this is of a 500. So you can see the number of cycles to failure for the control mix was somewhere around this one, which was nearly 9 lakh cycles, I can say. And then with G60, it was almost increased to 11 lakhs to 12 lakh cycles. Others also, which was a bit higher than the control samples. And then if you see at 200 microstrains, the stress levels are more than 10 lakhs for the G60 or the polyester geogrid. When it comes to the glass fiber grids, it was also nearly 8 to 9 lakhs. And similarly, if you see for the 500 microstrain, as the strain level increases, the fatigue life also decreases. So you can see it was nearly 1 lakh for unreinforced section, and it was nearly 6 to 7 lakhs for the reinforced section. This says that the incorporation of the geogrids has improved the fatigue life of your pavements. And these are the fatigue test results, and then this is the fatigue equation for the control mix. So based upon the equation, we can calculate the fatigue life of a pavement at any strain levels. So when this will be useful for doing the payment analysis during our payment design and all. And this is for our G60, the polyester geogrid at 20 degree. And these are our fatigue improvement factor. So you can see it was nearly 3 times improvement when compared with at 500 micro strains. It was nearly 3 times more than the control section. Even the polyester geogrid with backing also has shown nearly 1.9, and this is also 1.9 for the glass grids, and for the glass grid with backing also almost same. We got high improvement more than 1 time. So we've seen we have a good improvement in terms of rutting and the fatigue, and then we want to do a cyclic compression test on the pavement. This one test will give you the actual loading condition of a traffic. So here you can see a UTM was used to do the test, and then we have prepared a gyratory samples of 150 dia. So here we'll place this in a temperature cabinet where we can control the temperature. This test is done at 40 degree. I would just want to tell the image here. This was a SCB test, the semicircular bending test. Just for the we can change this attachment, and then we can this instrument has a facility to do all kind of tests like a resilient modulus or the dynamic modulus or the triaxial semicircular bending. Even the Marshall we can do, and the cyclic compression. Just we need to change the attachments. Similarly, our semicircular or the cyclic compression test attachment has been placed inside this one, and this is having a diameter of 100 mm. Solid disc is placed on this one, and then the cyclic loading is applied. We applied a 700 kPa load on the specimen for 1 second, and 1 second will be our rest period of 100 kPa, and again the loading will be applied for 1 second of 700 kPa. This is just a cyclic loading is applied on the specimen, like a square loading is applied. And we did this test at 2 different types of stresses. One is at 1400 kPa, which is very high, which is practically that kind of load will not be there on a payment. But still, we want to check whether the geogrids was going to sustain that much load. And then we did at 700 kPa, which is a standard for our design, which is at 560 to 700 kPa, which we consider for our payment design as per MEPD models. So you can see this is for the control mix, which is failed nearly at 1200 cycles. When it comes to the geogrids, the geogrid G, the glass grids like with backing was failed nearly 3000 or sorry 2500 or something. When it comes to the glass grid without backing, it was nearly 5000, and this one was 5500 for the polyester geogrid with backing. And without backing we got more than that one, somewhere around 7000 cycles it went. And similarly at 700 kPa stress, we can see even after 20,000 cycles our geogrid specimens are not failed. Where it comes to the unreinforced or the control mix, it was failed nearly 9,000 or 9,200 cycles. This says that by placing a geogrid, we are going to improve our permanent strains. And one thing I need to mention, the failure criteria for this test was 4 to 5 strain percentage. Suppose we have a strains has started at 0.1 micron for 1 cycle, our strains will increase as your cyclic loading will increase. So whenever the loading condition has reached more than 4 or 4.5 percentage, we'll consider that as the sample has been completely failed. This is our failure criteria for the cyclic compression test. So you can see at 700 kPa stress, Even after 10,000 cycles, it was less than 2% strain levels. And you can see the test specimen after the test. This is unreinforced test section. You can see the clearly the cracks has been formed, and there was a depression, the complete depression of strains, which is 5% or nearly 5% strain has been accumulated on the specimen. And then this is a specimen with a geogrid reinforcement. You can see slight cracks are there since at 1400 kPa the specimens are already failed, but still that was not that much visible when compared for the unreinforced or the controlled specimen. So after the test has been done, we have checked the geogrids, how the geogrids are there after placing, whether there is any damage to the geogrid. Then we have exhumed the geogrids without damaging to the geogrid by placing the specimen in a oven at 60° for 4 to 6 hours, and then we split the specimen to check the damage to the geogrid. You can see the polyester geogrids are good and intact. When then there was a some particles like asphalt and the tack coat is visible. And when it comes to the glass grids, we can see some sort of damage was there. So we can clearly see at this junction the geogrid has been damaged. So then we thought need to do a installation damage test on our geogrids. So suppose if you place a geogrid and during installation itself, if the grid has been failure, or how we need to check that one. So the whole purpose of this research will be negligible if the geogrids are failure even before the installation. So just we need to check that one. If the installation damage is there, then how to reduce that one, and if the installation damage is there, how to incorporate that in the design, or how much installation damage is going to happen, that we need to check this one. So accordingly we come up with a laboratory installation damage test. So the sample preparation which we used with our slab compactor, we placed the geogrid in the same fashion. Here we kept a constant, the load 600 kPa, and the number of passes for all the geogrids we have come up with a 25 number. After that has been done, we remove the sample from the mold, and then we split the two layers by placing at 60° for 4 hours in an oven. That we maintain a standard procedure so that it won't affect the properties of the geogrid during exhumation or during the heating. And then we have exhumed the specimens. These are the geogrids before installation. These are the geogrids after the installation. So the 4 geogrids which we discussed earlier. And then we cut it into, as per the required dimension. So here at the center, we made a cuts of this specimen. Yeah, these are the nothing but the at the center of the specimen, which are required dimension to do the tensile strength test for the test specimens. So this is a tensile strength instrument, which usually a UTM will be used, and we'll place the grid in between this one. We'll pull it off and see what will be the ultimate tensile strength of the specimen. And you can see the before the testing, this is the control specimen tensile strength, which is nearly 43 for the G50 and 56 or the 50. It was a manufactured product. So for G100, the glass grid was nearly 100. And after the test has been done, the installation, then we are exhumed, and then we did the tensile strength test. This is the average of 3 specimens, can say, and then these are the values. And this is a reduction. We can see clearly there was almost 25 to 30% reduction for the glass grids. When it comes to the polyester grid, it was nearly 10 to 15% reduction. So this shows that there was an installation damage was clearly visible for the geogrids. To place a geogrid, that's going before the traffic comments, there was a reduction in the strength. So now we need to see this parameter, how we can accommodate in our designs. Suppose there are different types of designs are there. Like if you place a geogrid, we consider the modulus improvement factor is a one kind of design we will take, or the TBR or the traffic bearing ratio we'll calculate, and then we will reduce the thicknesses, or we will reduce the, I mean, based upon the traffic load, our things, we will design the pavement by placing a geogrid. Suppose if the geogrid is designed for 50 kilonewton, and then you got at nearly 40 kilonewton as of the strength before the traffic load has been come, then we need to find we are in a discussion with the industry, and also the design parameters will be made in such a way the installation reduction factor will be considered in the design. And this is one the research which we done in the laboratory, and then we will need to see the field installation. So what are the challenges we are going to face when we are going to have a geogrids in the field. So one trial section which we laid in May 2025 in Mumbai. So this is a small, I can say this is not a trial section. I can say it as a trial patch of a 15-meter of a geogrid has been laid. Here, basically, we want to see what are the challenges we are going to place during the installation. So I can say we faced a lot of challenges, like there was an entanglement of a grid to the paver, and how we need to apply a tack coat on the geogrids, and the supervision of the labor which who are going to lay the geogrids. Initially, in the laboratory, we can see there's a small section of 300 by 400 we can easily lay. But here the geogrid will comes in a roll of 50-meter length and 3.3 to 3.75-meter width. So you want to lay that roll on a pavement which has its own challenges. So that we have been experienced during our field trials, and also at some places we have challenges issues, the asphalt material which goes below the grids, and then we are addressing that issues during our trial sections. So you can see this is a tack coat application, the paving has been done, and then this is a compaction of the surface layer, and this is after the grid has been laid. And one more trial section recently we are laid in Mumbai. This is a state highway, I can say. So here, going from Uran to Panvel Road, it has a, I can say, the lot of traffic, truck traffic has been there since the port material, or the material from port Mumbai port to Goa. This was a connecting road. So we can say the traffic of nearly 20 to 30 MSA will be there in this location. These are the I mean, the specifications, or the what are the materials we have used in our trial section. So same, we have used two grids. One is a polyester grid of 100 kilonewton and the glass grid of 100 kilonewton. And then we have two mixers of DBM and BC, which are 60 and 40 thicks. And we have used a RS1 tack coat in this field trial, and the field trial length is of 150-meter and the width of 7-meter. We divided into three sections of 50-meter with one polyester grid, and 50-meter with a glass grid, and a 50-meter of a grid, control section. So this is a proposed thing combination which we have used, the existing pavement and the DBM and the BC. And one more combination we are going to plan in the next month, which by placing a grid just on a existing pavement without any DBM layer. And these are the existing condition of the road. We can see the lot of the road has been damaged. I mean, whatever I got the information from the SIDCO, which is who is taking care of this road section, saying they are rehabilitating this road every year. But still the asphalt layer has washed out due to the rainfall and the heavy traffic, and this is the present condition of the road. And then we did this is the stretch which we have laid with the grid. So you can see the 50-meter stretch of the polyester. This went up to here, I can say. So in between, so this is total of 150 meter up to this level, I can say. And then backside also there was another 20 meters road was there. So somewhere here we have a geogrid laying, and then we have a control, and then we have a other geogrid, the glass grid also. And these are the two geogrids we have used with the backing. The one is a polyester geogrid and the glass fiber geogrid. This is a this grid, I can say there was a backing on the both the sides. This was come up with the industry based upon their experience. They want to have a backing on the both the sides so that the installation damage can be negligible. So the industry has manufactured this type of glass grid with 100 kilonewton and the polyester grid of 100 kilonewton. You can see the, as I said earlier, the biaxial grid and the uniaxial grid. Biaxial grid, nothing but we have a tensile strength from both the directions. The grid is weaved or knitted in such a way, you will get strength from both the direction. Whereas in case of uniaxial, you will get the tensile strength only in the machine direction. So this is a field trial which we laid. So the surface preparation has been done. The whatever the existing mm, uh, loose portion has been removed with the scraper, and then the tack coat is applied on top of that one, and the DBM layer is laid. This is a we made it in two patches, like a 3.5 meter width, because we want to allow the traffic to move in the one side. So 3.5 section was done at one side, and the traffic is left for the other direction. And similarly, the other side also DBM has been laid in that way. So once the DBM has been laid, and then we again applied a tack coat on top of this one. This is application of tack coat. So here I want to stress one thing: the geogrid of the tack coat application for the polyester geogrid was 0.4 to 0.5, whereas in case of the grid which has two non-woven backing, we went up to 1 to 1.2 kg per meter square. This is other research which we done with the industry for their specific geogrid. So the zero point 0.4 dosage is not giving a good bonding between the grid and the bottom layer and the top layer. So we have increased the dosage to 1 to 1.2 here. So you can see the lot of residue binder was there for this grid, this section of geogrid, the glass grid. So this is the laying of the geogrid. Once this the grid has been laid, uh, so the two type of grid, one is the white color one was two backing was there, and then which has a tensile strength of 100 kilonewton, and this is a polyester geogrid. So this is how the paving has been done for the two grids. So they are, as I said earlier, the challenges are there. Here the workers who are dealing with these things are inexperienced, so they don't have an idea how to lay the grid, and so we can see the small undulations on the top of the surface, which should be avoided, which we learned in our the field trial sections, which will we document, and then we'll share it with the industry so that these things will be taken care in further. So this is a finished layer of BC2, or once the asphalt grid payment has been done. On this payment, we are going to monitor it for another next 1 year to check whether any visible cracks or the rutting has been there, or we are planning to do a FWD or LWD test on this one to check the modulus, and also we are planning to take course on this one to check the how the performance is there, and also we are going to check the interface bond friction of exactly the field trial material, so which we are planning. And then when it comes to conclusions, I can say, of course, it's feasible to incorporate geogrid in asphalt pavements, and the tack coat is playing a influencing role in the geogrids. With rate of tack coat will be depending upon different grids require a different dosage of tack coat. And then we found another thing that RS1 tack coat may remove the bituminous coating on the asphalt, the grid. So that we need to check in further. So we want to check with different types of tack coat, whether the tack coat itself is degrading or the aggregates are puncturing the grid. By our installation damage test, we need to find that one. And then the grids are improving the laboratory performance by more than 100 percentage, but still we need to keep a cap in the design because the installation damage is there. So how we can improve the design and whether we can improve the life of a payment or whether we can reduce the thickness, that will be conscious decision we need to take from the project to project. And the field trial, what we find was the proper supervision is required, and the geogrid should be laid in tension, and the undulation should be removed, shouldn't be there, and we required a experienced person to do the installation. And apart from that one, there are a lot of challenges when there was the curves will come because the roll when we are laying it, it will be a bit difficult, challenging when the geogrid is laying at the curves. So this was when it comes to the project, it was funded by NTTM, and our industrial partner was Strata Geosynthetics and Ashwini Infra Developments. So thank you so much for the inviting me for giving a talk on the Geogrid reinforced asphalt pavements. And also I would like to thank Dr. Gautam Saran sir. He is my PhD guide, and I want to have this occasion to thank him. So thank you so much.
That was a nice presentation. Thank you, sir. Now the forum is open for discussion. Sir, I have a doubt.
Yes, madam.
Sir, you designated the geogrids as G60 and G50.
Yes, madam.
What is that 60 stands for?
No. 60 is just we given as a name to our grids. That's it for our research purpose. Both are having a 50 kilonewton per meter width of strength, and
Okay.
one is with
Packing.
backing and other one without backing. So when we started our research without backing, we, of course, the backing is also having their own issues. Suppose the backing material is not adhering to the geogrid, that is also creating a delamination. Maybe because of that reasons, we have seen a lesser strength in terms of rutting and fatigue values for the backing material when it compared to without backing.
Okay, thank you, sir.
Yes.
This is Wilson. I'm working in NATPAC. It was
Yes.
a nice presentation and it is a nice work. It was a nice work. Okay, I have one doubt. Actually, you have decided to keep the geogrid in between DBM and BC. How
Yes.
did you decide that this is the better position?
So we want to have as close as to the traffic load, since already we are using the geogrids in the foundation layer. So that was not that was improving that different properties, and also initially we done it with keeping at lower levels, like we can say in between less more than 30 mm of BC2 layer, of somewhere around 50 mm. The top layer will be 50 and the bottom layer will be somewhere around 30. But that was not giving a right results. It was performing better for control and also this one. So here, why we want to have just below the surface layer, in the sense, whatever the traffic loads are coming, that the geogrid will act as a reinforcement at the top level itself. So the load transfer will be done at that level.
If I would say that actually it is the better position is below the DBM, then how can you challenge this? My comment.
Yes, I understood. But when you place, that is also a good option. But when you have at such a lower levels, whatever the traffic loads we are getting, the top layer will be damaged before the whatever the loads reaches at that position, the grid, the reinforcement. So if I want to say the rutting test or the fatigue test, we can see at the interface, the bottom layer has been damaged if there was no grid. So
Okay.
if you place at the bottom level, the bottom level will also, the load transfer will be there, and if you place it below the DBM, the top level will get damaged. So here I can say we just need to resurface the top layer itself if there was any damages are there. Unless if you place it below the DBM, we need to remove all the DBM and the BC.
Okay. I have one another question actually. That you have laid the geogrid, and what was the this over? I mean, but this actually the two geogrid layers. I mean, one geogrid layers are. I mean, there is a overlap is there, no? And then in between two.
No, sir. No, sir. I actually forgot to mention that one. The Geogrid roll length was 3.75. So
Okay.
because that's a whatever the manufacturer has certain lengths of the whatever the machines they use. So they made it 3.75. So the total will be 7.5. We have to cut extra 0.5 meter at the edges. That's the challenge we have faced. And we didn't go for the overlapping in our field trials, because when we are overlapping was there was a chances of getting the asphalt mix below that one. So we placed both the two 3.7, 3.5, 3.5 at the touching without overlapping.
Okay. Thank you.
This is Srijit from NATPAC.
Yes, sir.
I have a small question. Actually, I missed the last part. I had a call. So you have shown that field applications, you have constructed some stretches over there.
Yes, sir.
I just want to know that whether this would be applicable for the distress payments for the overlay conditions or for the fresh payment, new payments.
Actually, this was applied on a distress payment only, sir, because already I can, 1 second. So we can see this is the existing condition of a payment which was distressed, which is a DBM has been washed out. Every year they are relaying it with a fresh DBM layer and all these things. So from Sitco we got this stretch. So this is how we done removing the top surface, and then the DBM has been laid, and then we have made this one. That's what one more combination we are planning to do, just by placing on the distress payment the Geogrid, and then just laying the BC layer. This combination we are planning in the next month.
Okay.
This is a distress payment. Actually, even the Sitco, which is a authority engineer, they are also saying the same issues has been facing from the last 10 years, I can say. So this is a condition of the payment before the scrape, the surface preparation.
So is it have you checked the subgrade condition? Is it because of any unevenness in the subgrade level or something?
No, sir.
Or only
Subgrade.
due to the fatigue failure?
The subgrade was very good. Even the CBR, we have checked the CBR, that was nearly 10 or something. The subgrade was okay. There was no issues with the subgrade. The only due to the high traffic and also there was a hilltop was there. Because of that reasons it was washed out and the traffic load.
Okay, okay. And one small question that is regarding the modeless input. Have you checked in the laboratory like any modeless improvement after the GeoGrid applications?
Yes, sir. We did the dynamic modulus test for the geogrids. So if I can show that one. 1 second. I will
So
share
it
the.
would be good if you conduct an FWD, just our so we'll be getting the real modulus after the construction also.
Yes,
That
sir.
would
Yes,
be
sir.
also great. Okay, thank you. It's a good presentation.
Yeah, thank you so
Thank
much.
Hello,
Hello.
this is Chandra from NATPAC. Actually, since we are placing this geosynthetics or geogrid in a bituminous layer, what is your view on the recyclability during any rehabilitation work? How it will be reused or recycled?
Actually, the plastic can be recycled, sir. That's not going to be an issue. But still, we are finding a way how much the top layer can be removed based upon the distress. Whether we can, without damaging any geogrid, we can uh, remove the top layer.
Okay.
That we are working on that one, sir. So the modulus I can, yeah. No, is it visible, sir?
It's visible.
Yeah, this is a dynamic modulus test we did on the specimen, which is having two layers of DBM and the BC. And then we placed a geogrid here and one without geogrid. We can see the dynamic modulus has improved significantly. And then after the dynamic modulus, we did the flow number test also. So this is at 35-degree temperature. So we're placing the LVDTs here. Yes, sir. And then based upon this one, we did a basic pavement design with the 200 MSA, how we can reduce the thickness and all as per IRC guidelines also.
So, is there any more questions from audience? If not, we can wind up the session. Rashmi, you can.
Now, I request Mr. Shijit PP to propose the vote of thanks.
Good afternoon, all. On behalf of KSCSTE-NATPAC, I would like to express my sincere gratitude to each one of you for joining the 32nd TransPedia research talk on the topic performance of geogrid reinforced asphalt payments. It has been a highly insightful and engaging session. At the outset, I would like to convey our sincere appreciation to our distinguished speaker, Dr. Lekhaz, Senior Scientific Officer and Head, Soil Mechanics and Asphalt Material Division, the Bombay Textile Research Association, Mumbai, for delivering such an informative presentations. Your detailed insight on the laboratory performance of geogrid asphalt payments, along with their roles in load distributions, reducing tensile strain, and enhancing the resistance to rutting and fatigue crackings, have extremely valuable to our research community. Your discussion on the practical challenges during the field installation also provided important takeaway for the real world implementations. I also extend my thanks to all the participants, including the transportation professionals, engineers, researchers, students, and industry experts, for your active participation and meaningful interactions. Once again, thank you, Dr. Lekhaz, for delivering such wonderful and informative presentations. Furthermore, especially thanks to our director, division heads, and the TransPedia coordinating team at NATPAC for their continuous support and seamless organization of this event. We look forward for your participation in our upcoming TransPedia research talks, as well as we continue to explore emerging trends and innovations in the transportation research. Thank you. Thank you all.
Okay.